Okay, practical skills uncertainties quiz. Here are the answers and me going over the answers. So, question 1 asks you to find out the percentage uncertainty in x. So, we've got a formula here. X is equal to 2 times by lambda times by y divided by z. The constants don't carry any uncertainties, so we ignore the 2. It's multiplication, so the variable of lambda is multiplied by y, and there's a division here by z. Now, we know division or multiplication, we add percentage uncertainty. So the percentage uncertainty in x is the sum of all of the percentage uncertainties. So it's percentage uncertainty in lambda plus what percentage uncertainty in y plus the percentage uncertainty in z. All of these have been given, so just add them all up and I get 15.05%. So I look for 15.05. It doesn't seem to have 0.5 on there, but 15, close enough. Moving on, should really have 0.05 because that's there as well. But because it's tiny in comparison to these, I think the examiners has gone said that's negligible. But nevertheless, it is 15.05 based on the data. So the answer is B. Question 2. They give you the length of the side of a cube, which is 2 centimeters, and they say that the uncertainty, the percentage uncertainty on that length is plus or minus 4%, and they give the mass of the cube of 24 grams plus or minus 8% uncertainty on that measurement. So what is the percentage uncertainty on density? So we know density is mass divided by volume. Okay, so we haven't been given the volume, but we've given the length. So to find the volume, we do the length cubed because it is a cube. So the density of a cube is the mass of the cube divided by the length cubed. So when we look at this, to find the percentage uncertainty of the density, it is because it's divided, mass is divided by volume, mass is divided by length cubed, you add the percentage uncertainties. So there's percentage uncertainty in mass plus the percentage uncertainty in length, but we multiply the percentage uncertainty in length by a factor of 3 because of that power there. So therefore, the percentage uncertainty in mass, 8%, given to you here, plus the percentage uncertainty in length, given here, times by 3, gives us 20%. So there's the answer, 20%. So here is division and a power. So division, add the percentage uncertainties, power, multiply that variable's percentage uncertainty by that power, and add them all up. Right, question 3. So here we've got, so this is a tricky question because they don't talk percent, but they talk fractions. Fractions and percent, the only thing that's different between a fraction and percent is the factor of 100 when we multiply it out. So it says that the student measures the radius r of a sphere with an absolute uncertainty delta r. So if we wanted to write it out, that could have been a number, right? Okay, so rather than write a number, they've said that the uncertainties are, and the uncertainty on it is plus or minus delta r. Okay, so normally that would be a value, let's say 3 centimeters plus or minus, let's say 0.2 centimeters, but they haven't given that. They've given it in this form. So what it says is, what is the fractional uncertainty in the volume? Well, we know it's a sphere, so a volume of a sphere is 4 over 3 pi r cubed. The percentage uncertainty, so if I was to work out the percentage uncertainty on that, it will be the uncertainty divided by r times by 100. Okay, but they are looking at fractional uncertainty. So you don't multiply by 100, you just leave it as delta R over R. Okay, so when we are looking at fractional uncertainty in volume, if we were looking at percentage uncertainty in volume, all we would have done is this doesn't have any uncertainties, a constant. That doesn't have any uncertainties, that's a constant. So the percentage uncertainty in the volume is 3 times the percentage uncertainty in the radius. Okay, so we are not looking at percent, we are looking at fractions. So the fractional uncertainty in volume is 3 times the fractional uncertainty in R. And we said that the fractional uncertainty is delta R over R. And we just put that there. So it's 3 times the fractional uncertainty, which is this here. Okay, this question, parallax error. This is the type of question that's referring to parallax error. So I've included this in there. So the diagram shows an analog meter with a mirror behind the pointer. So essentially you have got a pointer. Let's say I'm looking sideways on. There's a pointer. Behind the pointer, there's a mirror. Okay, so there's your mirror, let's say, behind the pointer. Okay, and when you look, you're looking for in this direction, let's say, sorry. Let's say you're looking from over here. Let me rub that out. Okay, so you're looking at the meter. There's the needle in front of you. You're looking sideways on. So there's the mirror. Okay, then these are the scales, and then let's say the mirror is right there. Okay, now if I was to look dead on, dead straight, what will happen is you will see that the pointer will be directly behind. If I look where my eyes are in this position, the mirror's reflection will be directly behind the pointer. But if I was to look from an angle, let's say my eyes are over here and I'm looking at the pointer, which is actually over here. If I was to look from this direction, I would see that the reflection of the mirror is on this side. So that means I'm not looking at this device correctly. So there is an actual error in the way I'm looking. So what it's trying to say is that when you do find yourself in that situation, move your head's position so that it's perfectly in line. So it's trying to say that you're measuring your value from the wrong place. Okay, now to reduce the risk of parallax error when reading the scale, so it's there to notify you that you're not reading from the correct place. Move your head. Okay, now question 5. Okay, this is where some of you asked how do I do this question. So I'm going to start off here. Okay, so it gives you the length of the cube, so at this distance here, and the diameter, so the diameter of this sphere. They say that it's the same. So what you have is a ball inside a cube, but the sphere is touching the edges because the diameter of the sphere is the same as the diameter of the cube. Okay, so I've written that out here. Diameter and length of the cube and sphere are the same. The radius of the sphere will be half the diameter, so it will be 5 centimeters. However, we discussed that we have to halve the uncertainty on that as well. Okay, so 0.1 centimeters is the uncertainty. That's key there. Now, the volume of the cube is the length cubed, and the volume of a sphere is 4 over 3 pi r cubed. Now these are required for them to move forward. So percentage uncertainty in the sphere is 3 times the percentage uncertainty in the radius, because it is a percentage uncertainty in the radius multiplied by the power. There aren't any other variables, so we don't add anything else. These are constant, so we ignore those. And that ends up being 6%. Then the percentage uncertainty in the cube is 3 times by the percentage uncertainty in the length. Again, that works out to be 6%. So if we were to look at the ratio of the percentage uncertainty in the sphere's volume divided by the percentage uncertainty in the cube's volume, we worked out that 6% for the sphere, 6% as a cube, 6 divided by 6 is 1, so the ratio is 1. Okay? Key to note is that the uncertainty is half. Okay, when we divide by a constant. So to go from diameter to radius, we divided by 2. So we divided the diameter by 2, but we also have to divide the uncertainty by 2 as well. 6. So here's the formula for finding a volume of a cylinder. Now, the question is find the uncertainty in percentage uncertainty in the radius. This is percentage uncertainty. So in the radius, I think they forgot to write percent. So here we've got a formula that's got V as a subject. The first thing we need to do is rearrange that formula to get R as a subject. So here I've rearranged the formula. So R equals V over pi times H all square rooted. Now, square root is a power of a half. So what I've done is I know the entire thing is multiplied by a power of half, so I've just added all those in. Now, we know that there's some division here, and there are some powers as well. So we're looking at percentage uncertainty. So the percentage uncertainty in R is the percentage uncertainty in the volume plus the percentage uncertainty in the height. Okay, because it's a division. But each variable, volume and height, carry this power of a half. So we need to multiply the percentage uncertainties by that power. So there's a half times that and a half plus a half times the height. So that's a half times 10%, which was the uncertainty in the volume. Okay, plus half times 6%, which was the uncertainty in the height. Okay, that was 6%. So that ends up as 8%, which is the answer D. Okay, question 8. So here we have a formula for angular momentum. Doesn't matter if you have done angular momentum or not. Regardless, the formula is there, so that's going to help. So this is a constant. So the only variable, because it's 1 divided by t, so that's t to the minus 1. We don't really... so that is 2 pi t to the minus 1. Okay, so when we're working out percentage uncertainty in omega, which is the angular speed, it is, look at the variables, that's only time. So it's a percentage uncertainty in the time. You can multiply by minus 1, but timesing by 1 or minus 1 doesn't really affect the value, the size of the percentage uncertainty. If you really wanted to do, you can add the minus, but remember it's plus minus, so that doesn't make a difference. Okay, so when we do the percentage uncertainty in omega, is essentially the percentage uncertainty in t. Okay, so here we've got The percentage uncertainty in T is 5%. So that's going to be the percentage uncertainty in omega as well. So that's 5%. Question 8. Here we've got an object in a gravitational field. The gravitational force, which is weight, acting on the object is 3%. So we've got weight. The uncertainty in the mass, m, is 9%. So what is the uncertainty in the gravitational field strength, g, of that field? So what formula do we know that connects weight, mass, and gravity? Okay, g, gravitational field strength. So it's W, weight, equals mass times gravity. Okay, from GCSE we know that. And g is equal to weight over mass. Okay, so g is equal to weight over mass. So g, that's division. So percentage uncertainty in G is the percentage uncertainty in W plus the percentage uncertainty in the mass. Because it's division, we add the percentage uncertainties. They've given you both. The percentage uncertainty on the weight is 3%, percentage uncertainty on the mass is 9%. So 3 plus 9%, 12%. There we go. That's your answer. And question 9. They'll give you another formula. It's on oscillations. We don't really need to know the theory, but we just need to know the equation, which is given. Okay, so they say, what is the percentage uncertainty in the constant k? It's already rearranged so that k equals, so we don't need to rearrange anything, but we know that the square root is a power of a half. So I'm just going to write that formula out with the power of a half here. And the percentage uncertainty in k is a half times the percentage uncertainty in the maximum acceleration, A max, plus a half times the percentage uncertainty in x naught. Okay, so the amplitude, that's what they call x naught. Now, doesn't matter what they're called, but because we got the formula, we just look at the formula and we see that because it's division, we add the percentage uncertainties of A and X. But because there's a power of a half here, we do a half, and it's all to the power of a half. We do a half times by A max, percentage uncertainty in A max, and half times the percentage uncertainty in X naught. Okay, so here it's add the percentage uncertainties. Okay, so it's a half times by, you could do it a half times by, add the percentage uncertainties of A max and X naught first, and then times it by half. At the end, it doesn't make a difference. Okay, so here we get half times 12%, a half times 20%, and that's 16% as your overall percentage uncertainty. Question 10. We've got a sphere again. We know the uncertainty on the sphere is 2%. What is the percentage uncertainty? They should say percentage uncertainty, but because it's already percent, then we make an assumption it's percentage uncertainty. So it's asking for what's the percentage uncertainty in the volume, because the answers are percent, so we're assuming they're looking for percent. And they haven't given really any other information in terms of lengths apart from that there. So we know the volume of a sphere is 4 over 3 pi r cubed, because it's a sphere. So from there, that formula, we can see that's a constant. Ignore the constant. So it's the percentage uncertainty in R times by 3, because the power is multiplied by the percentage uncertainty in R, and we get the percentage uncertainty in the volume as a result. So 3 times 2%, and that's 6%, and there's your answer. Hope that helped. and understanding some of the questions that you may have found difficult.